When, when we tackle evolution of stars, we have to emphasize what is exactly controlling and governing the evolution of stars. And one of the main point of this chapter and also next chapter, which deals with evolution of high mass stars, is that stellar evolution depends primarily on the stellar mass. So the more massive the star is, let's see if I can show here, the more massive the star is, the faster its evolution takes place. So we have the table with the stars that are O and the stars that are M. So O and M stars, and it goes this progression in decreasing temperature O, B, A, F, G, K, M. So you go from high temperature stars in their surface to low temperature stars in their surface, so about 50,000 Kelvin all the way down to 3,000 Kelvin. So the mass of the stars also diminish. So these O stars are 60 times as massive as the sun and go all the way down to stars that are 20% as massive as the sun. And what we see is the main sequence lifetime, which means the time the stars stay in the main sequence, diminish. In fact, um, the stars, they are the hot stars, 60 solar mass stars, they stay in the main sequence few 100,000 years. Whereas the stars that are very cold, the M stars, can stay as much as several billion years in the main sequence. Our sun is supposed to be a main sequence star for as much as 10 billion years. So what govern the stellar evolution is the initial mass of the stars. And the reason is, as we study stars, is that the energy that maintain the stars bright, the energy is a result of thermonuclear fusion reactions that occur in the very stellar core. So we saw in previous chapters, the star's interior part are divided in the core, the radiative shell, and for the low mass stars, the convective shells, where convection takes place. So the core is the region where energy is produced. Energy is produced. So this energy will be produced at a faster rate for the massive stars and will be produced at the lowest rate on the coolest stars. So the more massive, the faster this conversion of mass in energy will be taking place. So this is a very important aspect of this chapter on the evolution of main sequence stars, more primarily the evolution of stars like the sun. See if I can go to another slides. Can I? Yeah, I can. Now, what is being shown here is what we learned also in previous chapters is the so-called Hertzsprung-Russell diagram, which relates for a given star its total energy produced or luminosity and the surface temperature. It so goes that you go from high temperature in the left hand side and the scale diminish to low temperature in the left right hand side. So 40,000 to 3,000, and the scale here is in Kelvin. And the luminosity here, which is the energy the star itself is producing, is given in logarithm scale. But the main point is when you get and you put together the information as far as surface temperature and energy production in the stars, you find that most of the stars, more than 90% of the stars, happen to be located in a region that has a very specific name, and that is the main sequence region. The main sequence region is a region where our sun is located. The sun is the main sequence. And the main point with respect to the main sequence is all the stars belonging to the main sequence are converting 4 atoms of hydrogen into 1 atom of helium as a result of thermal nuclear reactions, and producing at the same time neutrinos and energy, gamma rays. So this energy, gamma rays, is the one that flows outward in the direction of the atmosphere and is responsible for maintaining the star in an equilibrium phase. So what is the fusion reactions that I was commenting? So fusion reaction is the process by which energy is produced by the stars in their very core, is the one responsible for keeping the star shining for so long. If the stars were shining as a result of chemical reactions like we do in the laboratory, combining certain chemical elements and producing fire, stars wouldn't be alive for too long. Even if they were a big reservoir of chemical compounds that once in full reaction, they would produce fire. So this is not how the stars happen to be hot. Stars are hot and they radiate energy because they have fusion reactions going on in their very core. So they have sort of a clean power plant in their very core producing the energy they radiate. So somebody happened to be in, see what's going on. Hey Amanda, how are you?
Okay, how are you doing?
Good, good, good. I'm okay. So I'm going over the subject of this chapter. Do you want to ask any question? I was taping, but I can't stop taping if you want to ask question.
Oh no, you can go ahead and
Are you all right?
yeah.
Grades are good?
Yep, I got it. It's like a B. Thanks for having your class.
Oh, that's how I like it. That's very good. Wonderful. Okay, so I'm going back to the taping thing. Okay?
Okay.
All right. So basically, what I was commenting was with respect not so much, um, not only for low mass stars, but also high mass stars, what govern stellar evolution is fusion reactions that occur in the very inner core of stars. So 4 atoms of hydrogen, let's see if I can get the annotate. 4 atoms of hydrogen are fused into 1 atom of helium and a bunch of particles named neutrinos. And these neutrinos, they interact very poorly with matter. So once they are produced, they escape the star and they do not interact with the stellar layers. And eventually, they we have, for instance, in every square inch of our bodies, we have billions, in fact, trillions of neutrinos crossing by, and we don't realize they are passing through us because they are very of a poor interaction with matter. They do not interact with matter. But neutrinos, they carry energy, and but also as a result of these fusion reactions, gamma gamma rays, which are electromagnetic radiations rays, are produced, and these gamma rays, they happen to be the most energetic radiation there is in the electromagnetic spectrum. And these gamma rays find its way to the atmosphere by warming up the internal regions of the stellar interior. And, and that's why the stars happen to be stable in its volume. They don't contract, they don't expand, they are stable in what we call hydrostatic equilibrium. Hydrostatic equilibrium, indicating the stars are not expanding, the stars are not contracting, because there is a perfect balance between the weight of the star and the force that arises when the gas pressure produced by energy produced in the core um, attempt to expand the star. So what this figure is showing is when the star initiates its lifetime, it has about 75% or so of hydrogen, and the remaining is helium, and it has some trace elements of all the other atoms. Okay, but as the star evolves and as energy ended up being produced in the core, so the core start converting hydrogen into helium. And then if you look at the x-axis right here, the core, which corresponds to about 20% of the stellar core, or stellar interior. So the core start converting hydrogen into helium. And in the case of the sun is right now at this percentage here. So the sun's core, more than 60% of it is is uh, is 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 made of, or is populated by helium atoms. And these helium atoms were created by our sun as a result of fusion reaction. So the sun shines because of this fusion reaction. Now, eventually, in few billion years, the core of our star sun will be completely helium populated. And when that happens, the helium will not undergo fusion reactions. Helium can be fused into carbon and oxygen, is a so-called triple alpha process. But for the sun, the temperature that is available in the core for these fusion reactions is too low. It's about 20 million kelvins. It's a small temperature, and this temperature will not fuse atoms of helium into carbon and oxygen, so the star sun will not undergo a fusion reaction. So what happened when the core becomes completely helium populated is that this production of energy coming out of a fusion reactions in the core is halt, is gone. And then what happened? So when the core, oops, when the solar core becomes a helium core, this process will happen. The one that you can you see my slides, Amanda?
Yeah.
Yeah. So when this happened, if you think about the core, this is the stellar surface, and the core cannot undergo fusion reactions anymore because the temperature is not big enough to allow for fusion reactions. But the region surrounding the core, a shell surrounding the core, has enough pressure and high temperature so that fusion reactions take place, but not in the core, but in the region surrounding the core. And yes, these fusion reactions will convert hydrogen, 4 atoms of hydrogen, into helium plus energy and neutrinos that will escape. At the same time, because now the star is exerting a full downward force on the core, since the core now is supporting the entire weight of the star, so the core will contract, will shrink under the weight of the star. Why the core was not shrinking before? Because the core was producing energy as a result of fusion reactions. But once the core becomes hydrogen depleted, and being only populated by helium, the core does not produce energy any longer. So the core starts shrinking. Now, with the core shrinking, uh, one of the things we learn in thermodynamics is when you have contraction, gas contraction. I don't know why this is happening. When there is gas contraction, gas contraction, and by gas contraction, by gas, think about the core. Gas contraction gives rise to temperature, rising temperature. So the temperature in the core rises because the core is being forced into a smaller volume. The core is being pressured inward by the total weight of the star. So the temperature rises. And in addition, you have this fusion reaction going on in a shell surrounding the core. As a result, in an outburst of energy, a surplus of energy coming out of that region, core and shell, and forcing the star into some expansion. So when the hydrogen content in the core is exhausted, the contracts, core contracts, and the star expands. So these two things, kind of a oppositing action, happen. So core contracts the minutes its volume, but the star expands because more energy comes out of the central region, and this surplus of energy is responsible for pushing outward the external layers. Now, when the external layers expand, the separation between molecules and atoms increases, and then less collision will take place. The gas becomes cooler, and cool stars in astronomy is translated into red color. So in this phase, the star becomes what we call red giant. Why red giant? Because the star became red as the surface temperature diminished, and the star expands its size, it becoming a giant star. So let me show you something else here, if I have there. Yeah, I do have, but I think I have to stop sharing, and I have to show this other thing. Okay. So here's an example of what happened with the star in the HR diagram. So the star, like the sun, is somewhere here. So here's an HR diagram where the loop. Can you see this
Yeah.
simulation, Amanda?
Yeah.
Okay. So you have a luminosity and temperature in here. Our star sun is one that has. How come I can't? For some reason, I cannot move the cursor. What's going on? This. Hmm. Just a second. I think I have to power my tablet. Just a second. I will get a cord. Okay, so it should work now. Just a second. I don't understand. I'm plugging my tablet, but I'm not having response. Well, oh, there you go. Um, well, my tablet is not responding. I don't know why. Well, I'm gonna use my hand anyway. So you have the luminosity here, you have the temperature in there, and here's where our sun is. In the HR diagram, this red line corresponds to what we call main sequence, and the sun is somewhere here. Okay. Now observe the diagram in the left-hand side. This is the sun. This is any star that happened to be in there. Let me try to make this star like the sun. See that? So it's like the sun. So when the sun exhausts its fusion reaction, hydrogen fusion reaction in the core, the sun will move in the HR diagram this way, becoming a red giant star. So as a red giant star, the sun is going to be bigger, and that is represented in this animation by this bigger star. We don't see the whole thing, but also its surface temperature, the color changes. The color now is a little bit reddish. And then the sun goes.
Hello?
Hello?
Oh, I'm sorry. I just got in. I'm so sorry. I'm late. My name is Sharina. I'm using my iPhone because my computer
Oh,
is
no
not working.
problem.
So I hope this is okay.
No, it's okay.
It's
Can
my
you
first.
can you
Okay.
see can you see what we are doing?
I can't. I'm still. Let me try to do it another way so I can see what you're doing because I don't see anything.
Oh
So
yeah,
I'm gonna
you
get
gotta have a
out.
computer. I know you're using your phone. Yeah, but
Yeah.
yeah.
Well, let me try. Let me try again. Let me
So who
try
is
again, and
this? Who is this?
uh, Sharina Tankson.
Hey Sharina, I can
Yes.
I'm gonna upload all of these in a few minutes once I'm done. So you can check later.
Oh, okay.
I'm gonna put it in
Okay.
Canvas, and then you can check it out later. If you, so, don't get too crazy now.
Oh, okay. Okay. Well,
All
thank
right.
you so much. Thank you very much. Thank you,
Okay.
sir. All
Okay.
right. Okay.
All
Bye
right.
bye.
Take it easy.
Okay.
Okay. Bye. Okay. So put this away. So here is the sun as a bigger star, evolved star, and then the sun once the the sun expands and the core heats up to the point that becomes 100 million Kelvin, which is a temperature good enough to initiate fusion reactions in there, then the helium in the core will be converted into carbon and oxygen, and then energy will be produced as a result of that. Now, the sun at that phase becomes, and I'm kind of jumping steps here, when these fusion reactions take place, the sun becomes of a constant luminosity. It's called horizontal giant branch star. Has this name horizontal because the surface temperature increases a little bit. So if I bring the sun to that position, see if I can do that. So this volume diminishes a little bit, and the star becomes hotter, meaning it's not as red as it used to be, as you can see in the animation. And once that phase is taking place, the core shrinks even longer as a horizontal branch. There is no fusion reactions in the core, but there are shells where hydrogen fusion reactions and helium fusion reactions are taking place. And then eventually uh, the sun's core reach temperature where fusion reactions of helium can take place, and the sun is then classified as an G, B star. It's called asymptotic giant branch star. Asymptotic giant branch star. So the sun expands its volume. So let's see what that corresponds to. So the volume increases even longer. Look at that. Becomes redder, right? The color is a little bit redder. And when that moment happened, eventually the temperature, the whole concentration of helium in the core is exhausted because the star helium supply in the core that produces carbon and oxygen right here is going to be gone. Helium will be depleted. The ashes of helium fusion reactions, carbon and oxygen, will be the result. So the core will be a core of carbon and oxygen alone. And then what happened? Well, for a low mass star, this is doom days. There is no more enough pressure from the star to ignite further fusion reactions of carbon and oxygen. And as a result, the star ends its life at that moment. So the way this low mass star ends life is by eliminating and expelling its shells on periodical events, and the star is then labeled as a planetary nebula. Planetary nebula. So let's go back to the PowerPoint. And that's what I was showing here. As a red giant, the core is pretty much inactive, but there is a shell of hydrogen burning on it. And that surplus of energy is responsible for expanding the star, making the star as a red giant star. Okay. And as a red giant star, the core does not indicate any hints of fusion reactions, but the shell around the core indicates fusion reaction. And that's produces excess of energy responsible for expanding the star. So that is the red giant phase. The star comes out of the main sequence and then rises up in the HR diagram by reducing its surface temperature and increasing its luminosity, because now it's getting too big. Now, as the helium core shrinks, the temperature increases, and the shell and the star itself is expanding, although the core shrinks, and then eventually the core will be hot enough to allow for helium fusion reactions to carbon and oxygen. And then the star goes to a horizontal branch, and then eventually to an asymptotic giant branch when there is no more fusion reactions undergoing in the core. So those are the main steps in stellar evolution for a low mass star, and as well as for high mass star, the controlling agent of stellar evolution is the total mass content. More massive stars will evolve faster than low mass stars. Low mass stars will take longer. Okay. So those are the main points I would like to mention. And so how massive stars, as I think I posted the video last week, high mass stars, they evolve faster and they do not halt their fusion reactions in carbon. They go to further stage in which um, neon, silicon, and other atoms undergo fusion reactions to the point the core is an iron core and cannot undergo further fusion reactions. The core contracts at very high speed and the star expands in a short amount of time in a megalithic explosion that we call supernova. So supernova stars that are exploding, producing enormous amount of energy, several hundreds of thousands more luminous than the sun. Supernovae can be outshine the brightness of entire galaxies of hundreds of billions of stars, just to give you an idea how energetic these explosions are. And high elements, high mass elements in the periodical table, they are formed in this fusion, in this exploding event. Okay. So that's the main point of this chapter. And I wonder if you guys have any question. In fact, what I'm going to do, I'm going to stop taping now.